Monocular metric depth estimation remains one of the most stubborn challenges in computer vision. Given a single RGB image, you want to recover a 3D point cloud with real-world physical scale. But perspective projection is fundamentally ambiguous. Without multi-view cues or known camera intrinsics, scaling a relative depth map to metric space has historically relied on a single global factor. And that assumption fractures the moment your test camera differs from your training distribution. Enter FoundationGeo, a two-stage framework that fundamentally rethinks how we bridge relative and metric geometry. Instead of applying a uniform scale, it learns spatial, pixel-wise calibration fields that correct both scale drift and ray direction bias, while explicitly repairing the camera intrinsic distribution mismatch that has plagued zero-shot generalization. Let's be clear about the current landscape. Relative depth models have achieved incredible accuracy by predicting geometry up to an affine ambiguity. They nail local shape, ordering, and fine structure. But for robotics, AR, or physical reasoning, you need metric scale. Existing metric solutions generally fall into two camps. The first explicitly models camera intrinsics, either by normalizing them into a canonical space or predicting focal length. The second repurposes strong relative predictors using a lightweight global calibration module. MoG2 is a representative of the latter. It takes a high-quality relative point map and applies a single global scale. It works well, but it leaves two critical errors on the table. First, scale misalignment is strongly spatially varying. If you align scale patch by patch, errors drop monotonically toward the per-pixel limit. A single global number simply cannot account for spatially varying scale drift. Second, even with perfect scale alignment, point maps suffer from ray direction bias. The predicted 3D rays can be slightly off-angle, which introduces unavoidable 3D inconsistency, especially under domain or camera shifts. FoundationGeo tackles this by first building an exceptionally strong relative backbone. They initialize a vision transformer with DINAV3, which provides rich, context-aware tokens. On top of that, they train on a curated 10.2 million image corpus, spanning indoor, outdoor, driving, and synthetic domains. But data size alone isn't enough. They apply multi-scale local patch supervision to preserve high-frequency details, surface normal consistency to keep surfaces piecewise smooth, and edge-aware losses to maintain sharp geometric boundaries. The output isn't just a flat depth map. It's an affine invariant 3D point map, where each pixel predicts a direction and a relative range, along with a reliability mask that downweights noisy or unreliable regions. This first stage gives you a structurally faithful, globally consistent geometry prior that's ready for metric lifting. Now comes the core innovation. Stage 2 moves beyond global scaling by introducing two lightweight, learnable spatial fields. The first is a ray direction correction field. Here's the technical breakdown. Each predicted affine invariant point is decomposed into a range term and a unit ray direction. The network predicts a two-dimensional offset in the local tangent plane, orthogonal to that ray. These offsets are bounded using a tan parameterization, which keeps angular perturbations stable and prevents catastrophic drift during training. The corrected ray is then renormalized and multiplied by the original range, giving you a direction-refined point map that preserves scale while fixing angular bias. The second field is a pixel-wise scale map. Instead of one global multiplier, the network predicts a spatially varying scale field. To supervise this cleanly without entangling it with a point map head, they use a closed-form least squares target. They project the ground truth 3D point onto the direction-corrected prediction to compute the exact scalar that minimizes the reconstruction error. This target is clamped to a physical range, logged, and supervised with a Huber loss. The overall objective couples the metric regression loss with decoupled supervision for the scale field and ray correction, weighted to ensure these fields act as precise calibration modules rather than redundant geometry predictors. But even with perfect spatial fields, the authors found a residual gap in zero-shot transfer. Their diagnostic revealed a critical insight. Metric prediction is fundamentally coupled to camera intrinsics, specifically focal length. When test cameras fall outside the training focal distribution, the model's implicit scale prior becomes unreliable, leading to systematic over- or underscaling. They visualize this by plotting the top 50 most frequent focal lengths in their training corpus against benchmark performance. Datasets like NIAF2 and KITTI, which align closely with the training distribution, performed strongly. But benchmarks like DDAD, ETH3D, and Diode, which cluster in an undercovered 1000 to 1373 pixel focal band, suffered sharp accuracy drops. Rather than predicting focal length as an auxiliary variable, they took a purely data-driven approach. They built a Blender-based data engine to synthesize 23,700 additional images across 7 diverse scenes, explicitly targeting those missing focal regimes. They compared fixed focal rendering against diverse focal rendering, and the diverse focal set consistently improved cross-dataset robustness. This targeted intrinsic coverage works hand-in-hand with the spatial fields. The fields handle with an image spatial drift, while the diverse focal training aligns the model's implicit intrinsic prior, making it resilient to camera shifts. The results speak for themselves. On 7 zero-shot benchmarks, FoundationGeo achieves the lowest average absolute relative error and highest inlier consistency, outperforming heavier baselines by over 5% on average. More importantly, it doesn't just win on average, it's remarkably stable. Methods that excel in narrow regimes often degrade sharply on specific domains. FoundationGeo stays competitive across indoor, driving, and object-centric scenes. Ablations confirm every design choice. Two-stage training consistently beats single-stage metric learning. Spatial fields outperform global scaling. The decoupled field losses stabilize training by preventing head interference. And the diverse focal synthetic data directly repairs the intrinsic coverage gap. Even the redirection correction shows measurable gains in angular accuracy across all datasets, proving that directional bias is a distinct, solvable error source. FoundationGeo represents a meaningful shift in how we approach monocular metric geometry. It stops treating scale as a global constant and starts modeling it as a spatially varying field. It stops ignoring redirection bias and explicitly corrects it in the tangent plane. And it stops hoping dataset mixing will fix intrinsic mismatches, instead using principled, focal diverse synthetic data to close the gap. The result is a framework that generalizes robustly without requiring ground truth intrinsics at inference. For anyone working in 3D vision, robotics, or foundation models, this is a clear blueprint. Strengthen the relative prior, calibrate spatially, and design your data around the physical distributions that actually matter. The paper and project page are linked in the description if you want to dive into the loss formulations, tangent basis construction, or the full benchmark breakdown. Thanks for watching, and keep pushing the boundaries of what single-image 3D vision can do.